Welcome to the second part of the lecture. We're going to talk about solution strategies, and this part is focused on semi-inverse methods. We can take three solution strategies to find an analytical solution for practical problems. First, we can use the displacement formulation, or a stress formulation, or semi-inverse method. We're going to talk about them in details later. Also, we can combine them using principle of superposition. Before jumping into these different solution strategies, let's talk about principle of superposition. You remember that the field equations for linear elastostatics are linear in terms of the unknowns. As a result, assume that epsilon, sigma, and u are a solution for body force B1 and traction forces T1. And also sigma 2, epsilon 2, u2 are a solution for body force B2 and surface traction T2. Then we can say that sigma equal to sigma 1 plus sigma 2, epsilon equal to epsilon 1 plus epsilon 2, and u equal to u1 plus u2 offer a solution for the case that we have body force B equal to B1 plus B2 and traction of T equal to T1 plus T2. This is basically principle of superposition, and we find it extremely useful because we basically can find a solution, can break the loading into different cases, find the solution for each of them, and then combine the solution that will be the final solution in the case of all the loadings acting at the same time. As an example, assume we have a cube. It is like under traction 1 and like body forces B1. And assume that it results in a deformation like this. Assume the same cube, this time under traction 2 and body forces 2. And let's say it resulted in this deformation. So this is basically U1 and this is U2. Okay, if the same cube undergoes both these tractions, T1 and T2, and both body loads, B1 and B2, the resultant displacement would be the summation of U1 and U2. And we don't need to solve the problem again for the case of combined loading. Okay, let's get back to our solution strategies, and we're going to talk about semi-inverse method first. For simple problems, we can assume a stress field that satisfies the boundary conditions and equilibrium equations. You remember the equilibrium equation between stress and body forces. Then calculating the strain field using constitutive law, here Hooke's law. And finally the displacement field by integrating the kinematic equations, finding u based on epsilon. Let's try that via an example. Here we have a cube under uniaxial loading. The aim is to calculate stresses, strains, and displacement for any point x1, x2, x3 in this linear elastic cube. And we assume a uniform distribution of stress over the top and bottom surfaces. So, of course, we have a point load, F, acting on both ends, but assume that it results basically on a uniform stress distribution. Basically uniform stress. And also note here we have P equal to 0, so there is no body forces. Okay, first we start by drawing a sketch of the problem indicating all the forces and loads. You see it in the figure here. Note that x2 and x3 are aligned with the plane and x1 is outward. Step 2 is calculating stress boundary conditions using the relation T equal to sigma Ji and J. We know that all the surfaces are stress-free except for x equal to plus a divided by 2 and x3 equal to minus a divided by 2. Okay, let's work it out. Let's find a stress components based on the boundary conditions. For x3 equal to a divided by 2, the normal vector there is upward, so it's 0, 0, 1. And the traction vector there is again upward with value of f divided by a square. So it's f divided by a square multiplied by the vector 0, 0, 1. Okay, let's do it for each of the elements in traction vector. We know that T1 is equal to sigma 1, 1, N1 plus sigma 2, 1, N2 plus sigma 3, 1, N3. So N1 is already 0, N2 is 0, so basically it is equal to sigma 3, 1, N3. So we can say sigma 3, 1, N3 is equal to 0. So sigma 3 is equal to 0. For T2, we have sigma 1, 2, N1 plus sigma 2, 2, N2 plus sigma 3, 2, N3. Again, N1 is 0, N2 is 0, and n3 is 1, so we get T2 equal to sigma 3, 2, but we know that T2 is 0. So sigma 3, 2 is 0. For T3, we have sigma 1, 3, n1 plus sigma 2, 3, n2 plus sigma 3, 3, n3. Again, n1 and n2 are 0, and n3 is 1, and T3 is F divided by A2. And also, for boundary conditions on the other surfaces, we can find that sigma 1, 1 is 0, because, for example, for a normal vector of 1, 0, 0, for when x1 is equal to a divided by 2, traction vector is 0, 0, 0. So it results that sigma 1, 3, 1, 1 is 0. And also it results that sigma 1, 2 is 0. For x2 equal to a divided by 2, we get n equal to 0, 1, 0, and t equal to, again, 0, 0, 0. So it results that sigma 2, 2 is 0. Okay, you see that we've already found sigma 3, 1, sigma 3, 2, sigma 3, 3, sigma 1, 1, sigma 1, 2, and sigma 2, 2. And also, knowing that P is 0, using the equilibrium equation, it gives us basically sigma I. We can again see that sigma ij is equal to 0 for I not equal to j. Okay, the third step is obtaining a distribution of a stress tensor that satisfies these values that we found. And actually a simple one that we can think of is a stress tensor with all of the elements being 0 except sigma 3, 3. So it basically, we use the boundary conditions to find the stress components at the boundaries, and then assume and then actually think of a stress distribution that satisfies those boundary conditions, and this one pretty well satisfies it. The fourth step is calculating a stress tensor using Hooke's law. Here we have the Hooke's law in engineering form, and we just need to substitute sigma in Hooke's law to find the strains. Let's do it for epsilon 1, 1. It becomes 1 divided by E multiplied by 1 plus nu, sigma 1, 1 minus nu, delta 1, 1 is 1, and sigma, here we have kk, so it's basically a summative index. We have to repeat it 3 times. It gives us sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. That's the trace of the matrix. We know that sigma 1, 1 is 0. We know that delta 1, 1 is 1. And we know that this one is 0, this one is 0, and this one is F divided by A square. So it gives us epsilon 1 1 equal to 1 over e multiplied by minus nu multiplied by f over a square. For epsilon 1 2, we get 1 divided by e, 1 plus nu multiplied by epsilon 1 2 minus nu delta 1 2 sigma kk. Know that delta 1 2 is 0 and also sigma 1 2 is 0, so it becomes 0. The same basically for epsilon 1 3 and epsilon 2 3, which all become 0. For epsilon 2 2, we have the same as epsilon 1 1. It's basically 1e multiplied by 1 plus nu sigma 2 2 minus nu delta 2 2 multiplied by sigma kk. And we already know that sigma kk is f over a square. Delta 2 2 is 1, but sigma 2 2 is 0. So it results in minus nu over e f divided by a square. And finally, for epsilon 3 3, we have 1 over e multiplied by 1 plus nu multiplied by sigma 3 3 minus nu delta 3 3 sigma kk. Here you know, okay, this is sigma 3 3. Okay, here we know sigma 3 3 is f divided by a2 and delta 3 3 is 1. Sigma kk is the trace, again f divided by a2. So it is basically 1 over e f divided by a2, 1 plus nu minus nu. And we have plus nu minus nu, so it becomes just 1 over e f divided by a2. Okay, you see that we found all of the strain elements, strain tensor elements, based on stresses. And here it is, the strain tensor is minus nu f over e a square, and for epsilon 1 1 epsilon 2 2, and f over e a square for epsilon 3 3. We need to check the compatibility conditions are satisfied, but they're automatically satisfied for constant strains. And you see that we have constant strains here, meaning that they are not a function of position x. And the last step is finding the displacement field using the kinematic equations that we have. So, for example, for epsilon 1 1, we have it's equal to u1 1 or partial u1 partial x1, and we know it's equal to minus nu f divided by ea square. And if I integrated with respect to x1, I get u1 is equal to minus nu f over e a2 x1 plus a constant, which is basically a constant as a function of x2 and x3. For epsilon 2, 2, we have partial u2 partial x2. It's again equal to minus nu f e over a2. So u2 is minus nu f over ea square x2, this time plus a constant, which can be a function of x1 and x3, but not x2. And finally, for epsilon 3, 3, it is again partial u3 partial x3, which is equal to f over ea square. So u3 is equal to f over ea square x3 plus a constant, which can be a function of x1 and x2, but not x3. Okay, now we have the displacement u as a function of the forces, so that's the solution that we were looking for. But we have constants f1, f2, and f3. And that we use the boundary conditions, the displacement boundary conditions, and any additional symmetry that we have. For example, we know that at u1, u2, and u3 are 0 at x1 equal to x2 equal to x3 at 0. So basically, at the center, we don't have any displacement because of symmetry, because basically we elongated symmetrically from both ends. So we get a neutral plane passing the center. Okay, so basically at x equal to 0, x1 equal to 0, x2 equal to 0, x3 equal to 0, the strain should be 0. So basically if I set x1 to 0, u2 should be 0. Okay, this is u1. Okay, so if I set x1 to 0, u1 should be 0. That says that this term is 0 because u1 at x1 equal to 0 is 0. Okay, this one is 0 as well because again u2 at x2 equal to 0 is 0. And f3 is 0 again because u3 as x3 equal to 0 is 0. Okay, that gives us the three displacement relations we're looking at as a function of the forces and position. So u1 is minus nu f over ea square x1, u2 is equal to the same thing but with respect to x2, and u3 is f over ea square x3. Just pay attention that since it's infinitesimal case, doesn't matter if you use capital X or lowercase x. Okay, they're both frames matches. And that's the kind of deformation that we anticipate. Okay, there are some important notes to take home here. One is for a cube under uniaxial loading, we have sigma 33 equal to E multiplied by epsilon 33 in the x direction. So basically, using the Hooke's law, we can find E as a function of Lamé's constant or Young modulus. We can use it for experimental identification or measurement of E. Also, the fractional contraction are equal to Poisson ratio, meaning that basically the fraction of epsilon 1 to epsilon 3 epsilon 2 to epsilon 3 are equal to Poisson ratios, and Poisson ratios can be found based on Lamé constant. Again, that's another way to calculate Poisson ratio from experiments. And third, Poisson ratio is related to the volume change or dilation. We've already seen that dilation is epsilon, the trace of a strain tensor, and in this case it becomes epsilon 1 multiplied by 1 minus 2 nu. And it says that if the material is incompressible, meaning that delta is delta V is 0, it says that 1 minus 2 nu is 0. So for incompressible material, nu is equal to 0.5. And the solution is unique.